our first talk from Lucas, probing socioeconomic dynamics in high energy physics using the Inspire HEP database. Go for it.
Thank you very much. So due to time constraints, I will dive right into it, and I will also be very brief, but you may find a draft expanding on these ideas and the methodology on archive. All right. So my question is, can we address broad HPS questions, whether it be about high-energy physics, aka HEP in particular, or about modern large-scale science at large using quantitative methods? And in the following, I will present a case study, which is such an attempt. And for that, I will proceed twofold. First, so I will introduce Inspire HEP, which is a database focused on the big science that is high-energy physics. And second, I will use this database in order to address questions that were motivated by the HPS literature about the disunity of science. And the final claim that I will put forward is that particle phenomenology is increasingly deficient in bringing together the field of high-energy physics and challenging its unity. All right, so, okay, so first, some context. What is high-energy physics? Well, it's roughly speaking the study of the fundamental forces and entities of nature. And really the name stems from the fact that historically, the standard way to get knowledge about these entities has been to accelerate and smash particles at ever higher energies. But to do so requires large-scale experiments, such as the Large Hadron Collider at CERN, which involves about 10,000 collaborators. And theoretical work in high-energy physics is significant in scale as well, totaling to about 10,000 papers each year on archive. So high-energy physics is really the realm of big science, and as a result, the scientific activity in the field produces large amounts of data for historians and philosophers to analyze. So we might think that this poses a methodological problem, but I would argue this is instead an opportunity to elaborate statistical studies of science informed by concepts from history and philosophy of science. So as I will show in particular in this presentation, Peter Gallison's concepts of subcultures and trading zones can help design quantitative analysis for addressing the epistemic consequences of the division of labor in big science. So, all right. So Inspire HEP is a platform for high-energy physicists, which allows to search the literature, to list job offers, to look up upcoming conferences and seminars. So it really responds to the needs of the community. But it included a wide variety of sources for the literature. Archive is the main source, but it also gathers data from scientific editors. I do not know the precise amount, but it contains nearly 2 million records with a decent coverage of years 1980 to 2020. And some might say this qualifies as big data. So this database can be explored through an API. And why is it interesting? Well, first, as I said, it contains bibliometric data, abstracts, keywords, citations, authorship, affiliations, which benefit from manual creation. But what is more original maybe is that it goes beyond traditional bibliometric data. For instance, it contains career data about physicists, such as positions held, hiring dates, PhD advisors, etc. It also contains lists of experiments, their publications, their proposals, their initial proposals, their members, their operation history. And as a result, the database has been used in a number of previous works that go further than analysis of purely bibliometric data. For instance, it's been used in a number of papers evaluating the performance of experimental collaborations. And the hiring data has also allowed studies of gender inequalities in high-energy physics. So this paper in particular that I cited by Strumia is very controversial, but without endorsing it, it does show nevertheless that the database might be of interest to academics interested in quantitative studies of science. All right, so now I would like to turn to my own topic of study, which is the unity of high-energy physics. So there is a strong division of labor in the field of high-energy physics. For instance, experimentalists and theorists are distinct groups of physicists with different training, with their own jargon. And reason for this include the increased technical specialization, but also the increased size and duration of experiments, which provide full-time jobs to experimentalists for years and years. Now, in fact, there are three major categories in the literature in HEP: theory, phenomenology, and experiment, as classified in archives website, but also in the Inspire HEP database. And in order to visualize the division of labor between these three categories of the literature, what we did was that we analyzed the publication record of high-energy physicists and the fraction of how much they publish within each of these categories over a certain time range. And the results are shown on this ternary diagram. Each red dot is a physicist from some random sample, and physicists towards a vertex publish almost exclusively to one of these categories. And so as you can see, we find clusters at each vertex for each category, which means that each category has some sort of its own community. But we do see, however, that physicists combine phenomenological and experimental papers, and that some combine phenomenology with theory. So phenomenology seems to play a special bridging role for the unity of the field. All right, so what I'm especially interested in today is the distinction, between theory and phenomenology. So in constructing quarks, entropy King writes, I quote, "Particle physicists make an imprecise distinction between doing theory and phenomenology. The former refers to such activities as the abstract elaboration of respectable theories, the latter to the application of less dignified models to the analysis of data and as a guide to further experiment." So now I would like to use quantitative methods to further explore the separation between theory and phenomenology. And to do so, what we did was to train a model to predict the category to which abstracts of the literature belong using some logistic regression model. And with this model, we can find out which keywords discriminate the most between phenomenology and theory. And we do find the following keywords, which are revealing of different dimensions of the divide between the two. First, an ontological divide. On one hand, phenomenology is centered around particles, while theory is most concerned with space-time and strings. Second, phenomenology makes direct references to empirical data and concerns which theory does not. And third, we find a methodological divide in that phenomenology relies on approximate theories with a finite range of empirical validity, while theory relies on idealized theoretical components. So what we see is that theorists and phenomenologists are partially distinct groups of physicists manipulating partially distinct bodies of knowledge articulated by distinct languages. But how then are they able to communicate and exchange knowledge in spite of these marked differences? So Peter Gallison's proposal in his book Image and Logic is that scientific cultures communicate and coordinate with each other inside what he calls trading zones. And trading zones are drawn on an analogy drawn from culture and anthropology. Scientific exchanges are compared to trades between cultures, which may require the elaboration of an interlanguage. But for such trades to take place, there must be things that both cultures can value within their respective enterprise. And what Peter Gallison emphasizes is that it is not necessarily the case. He wrote, I quote, "There is no theological drive toward ever greater cohesion. It is altogether possible that at some moments, fields previously bound fall apart." So now the question for us is then, what exactly is shared between these two subcultures of physics, theory, and phenomenology? In fact, Gallison's framework motivates a quantitative analysis of the trading zone between theory and phenomenology. And for that, we will use the fact that citations across scientific cultures signal trades. Presumably, concepts that enhance such trades between theory and phenomenology should appear frequently in the abstracts of phenomenological papers cited by theoretical papers and vice versa. And in order to unveil these concepts, we extracted keywords from the abstracts of papers that are involved in such trades between 2001 and 2019. We can start with phenomenological papers citing theoretical papers, and we look at those concepts for which the probability of occurrence in the trading zone has declined or increased the most. In other words, what we see here are the transformations of the trading zone between theory and phenomenology. To the left, we observe a decline in theories that protected new physics at the energy scales probed in particle colliders, supersymmetry, extra dimensions, and the low energy limit of higher theories, Indeed, the LHC and previous experiments have challenged such models. And to the right, we see the increasing importance of new channels to quantum gravity, such as black holes and gravitational waves, for which new experimental opportunities have been opened up recently. We also see the increasing importance of dark matter. Now turning to trade of the opposite direction, theoretical papers citing phenomenological papers, what we see is again, a dramatic decline in trade involving extra dimensions, and second, a declining interest in stellar model physics. Finally, on the right, we see again an increasing interest in dark matter. So in order to, I would like to argue that these trends signal a significant shift in hydrogen physics. And in order to make sense of it, I would like to emphasize first that theorists prioritize epistemic goals such as the unification of fundamental forces, the pursuit of quantum gravity, the understanding of our fundamental theories, and the ontology of space-time. Phenomenologists, on the other hand, prioritize the explanation of empirical anomalies and the search for new phenomena. Now, developments in high-G physics, high theory, string theory, quantum gravity, etc., seem less and less able to promote progress in phenomenological particle physics using particle colliders. And the failures of extra dimensions models and supersymmetric models are notable examples of such difficulties. Conversely, larger particle colliders seem increasingly unlikely to provide guidance to high theory. So the training zone shifts away from particles toward astrophysical phenomena, black holes and gravitational waves, which may provide more direct views about quantum gravity. It might be, yeah, so just to conclude, so Inspire HF offers a variety of data and insights useful for the study of the big science, publications, hiring, experiments, etc. Quantitative studies of such data informed by HPS theories can help address questions motivated by the HPS literature. And finally, the exploration of the trading zone between two theoretical subcultures of high-energy physics reveals a major shift in the field from particle phenomenology centered on particle colliders toward astrophysical phenomenology using black holes, gravitational waves, dark matter, etc. All right, thank you for your attention. That was it.
All right, thank you so much, Lucas. Our next talk is going to be from Guillermo.
Yeah, I'm going to talk. First of all, thank you for accepting this contribution to this meeting. I have heard several interesting talks, and I'm going to talk about the computational approaches to the history of chemistry, and in particular, to the focus on the expansion of the chemical space. Then, as a motivation of the importance of chemistry is that if you go to the scientific literature, then you find that chemistry is along history one of the major fields in terms of publications. And you see here in blue the number of publications in chemistry. This is from the Easy Web of Knowledge. Then you see that only recently was surpassed by engineering, but in general in science is the most or the leading science in terms of number of publications. But it's also growing very fast in terms of the substances that are produced in chemistry, which is the currency of chemistry. Chemistry is about substances, and the substances are growing very fast. I'm going to come back to this picture later. But then the point is that how to address historical questions and even philosophical questions on the evolution of chemistry. Then what we have here is that the whole edifice of chemistry, all the production of substances, all the production of reactions, all those things are producing data in the end. Unfortunately, that amount of data is now collected in electronic databases, for example, in Reaxys and in SciFinder, which is heavily used by the chemical community, but not by historians. And then this is what our approach, and we think that those data sources are not only rich in chemical information, but also in historical information. And then the idea is to take the data and go to explore the history of chemistry, which is about the past. But as Tolstoy already mentioned, and it's a new trend in, for example, in the complexity studies at the Santa Fe Institute, it seems that there are some regularities. And for example, we have seen this in the first talk of today, for instance. There are some regularities along history, and then perhaps with some mathematical methods, we can try to understand them. That's more or less the approach we have here, and then I'm going to show some of the results in that direction. The idea is to combine mathematics, computer sciences, history and chemistry, and all the data, approach the data from those different angles, and to shed some light on the history of chemistry, but mainly on the evolution of chemical knowledge. And if we have data on that direction, then we can model, and if we can model, perhaps we can estimate the future of chemistry with error bars. But that's more or less the aim, and which is very important because of the important role of chemistry for society. That's something, a hot topic, I would say. For instance, in the new epoch of the Anthropocene, that's very important. Part of what I'm going to say here is it was published in this book along with Jürgen Jost, and the general setting we have for the analysis of the evolution of chemical knowledge is that chemical knowledge is a complex dynamical system, which is based on three interacting systems, which is the material system, the social, and the semiotic system of chemistry. In the material system, we have the reactions of the substances, along with the technologies that chemists have used all over the history of chemistry. The semiotic system is about the language, the theory, the communication channels chemists have to report their results and to communicate among them. And the social system is the institutional part and where the individuals are located. And then as a complex dynamical system, our aim is to try to find the simple rules of interaction of those systems. That's the final aim we have for this research agenda. Then coming back to this plot, what we did was to take all the substances reported in the scientific literature between 1800 and 2015, and we counted every year how many substances were reported as new substances. This is the plot we got, and we found an exponential growth. This is the equation, and you can calculate based on the slope of this plot, you can calculate the doubling time, which turns out to be 16 years. That means that in the following 16 years, chemists would be, if these trends are maintained, in the following 16 years, chemists would be able to double all the substances they have been able to make in the history, in the past history, in a single year, or in a single year, no, in the following 16 years. That's more or less the speed of chemistry. It's growing very fast. And this is material production. Now, another thing we did, and the results of this research were published in, here is the reference in PNAS. What we did was to explore how chemists have been using the substances of the chemical space. The chemical space is the collection of reactions and substances and the evolution of that collection. That's more or less what we have in mind. Then we explore in different periods of time what have been the use of those substances for making new reactions. Then in different colors here, you see different periods. And here you have the different periods. But what you see here is a heavy tail distribution. It's a heavy tail distribution telling us that in this part, what this tells us is that many substrates have been used only once. Chemists have substances, but they use them only once for making reactions. But there, at the other extreme here in the tail, you have that there are historically, the chemists have several substances, but very few substances, which have been used thousands of times. And here I have two examples of those substances with enormous use in the production of new chemicals. Now let's go to the side of the products. And on the side of the products, we also found heavy tail distributions, meaning that there are many products which have been synthesized only once. And chemists produce something new, and normally they don't go back to that substance. They want to find new things. But also there are some substances at the tail of the distribution, there are some substances which are often synthesized. Those are the side products of chemistry, CO2, water, but also some products of interest for the machinery of chemistry. Then in conclusion here, what we have is that chemists have made a frequent use of a few starting materials. Those are here in the tail of this plot. And they discover many substances, but those substances are not used anymore. That's more or less the way of exploring the chemical space. Now, how they select those substances they want to combine. Then we found that most of the reactions in the chemical literature span no more than three reactions, no more than three substances. And about half of them are made of only combining two substances. And to tell this in a very brief time, we found that one of those substances is heavily used. I mean, chemists know a lot of the chemistry of that substance, but the other substance is kind of new. This is what we call the fixed substrate approach. They try to combine couples of substances. One of those substances is very well known and the other is new. It's something like to try to get control of the operations they are doing. This is a kind of simple rule of interaction that we are aiming to have in the complex dynamical system. But we can do some numbers. And then, for example, those are the number of atoms in the universe. And there are several discussions about this, but we could say that the available substances we can reach according to our methods is 10 to the power of 200. And this is the possible number of chemical reactions. But 10 to the power of 200 substances is something like, if we know that chemists have been able to double the number of substances every 16 years, then we can calculate when are we going to be able to get to those substances. And I did the calculations, and what we need to get that is about 10,000 more years from the present. Then we are very far from completing the chemical space, and then Stephen Hawking would say that by that time we will be extinct. Then we say, okay, let's try to approach the completeness of the chemical space from another direction, and is that let's try to speed up the rate of production of new chemicals. And let's suppose that we want to get to that place, to this number of substances by 2050. In order to get to that number of substances in that time, that would require to have this doubling time, which is kind of crazy because we have more than 200 years of constant rate and exponential growth rate, but it has been very constant. But perhaps with new technology that could be afforded. That's something that with this data we can tell to the chemistry community. Then the question is whether we can fight against historical patterns or not. And yeah, I think I have 10 seconds or something like that. And this is the team working behind this: Jürgen Jost, Peter Stadler, Doug Lu. We use here a lot of time series analysis, for instance, and we have different statistical regimes in the production of new chemicals, but that's another story. Then thank you very much for your attention.
Great, thank you so much. And our last lightning talk of this session is Joel West.
Thank you. So my name is Joel West, and I'm going to be talking about a semiotic and narratological basis for understanding the relationship between data sets as signs or models and the information produced by machine learning. My roadmap is very simple. I'm going to be looking at the semiotics of Charles Peirce. Secondly, I'll be looking at the relationship of the sign to its object. And in this case, I'll be using the work of Umberto Eco, who's further developed Peirce's work. Thirdly, I'll be looking at narratology, which is this understanding how narrative discourse works. Fourth, I'll be looking at data sets as kinds of discourses. And finally, I'll be looking at semiotics and big data. And to conclude then, I will demonstrate that there is an ellipsis between big data, what it means, and how it is we can understand it. And that we can, in fact, understand these things as kind of a narrative that we create ourselves. So first of all, I'm going to start off with a little bit of technical stuff. I'm going to start with C.S. Peirce, who defines the sign for us, and there's two different ways. There's the French school, and that's of Ferdinand de Saussure. In this case, I'm following the American school, where he says that a sign is something that just represents something else for someone. But the important thing is that he says that it creates in the mind of that person an equivalent sign or a more developed sign. So the two things are not exactly the same, they're similar. And that it's in reference to sort of an idea is what we're saying, so that we have something that represents something else. And here I'm going to use an example. We have two triangles, and we can say that the two triangles are certainly equivalent. but we can't say that they're equal. One is more developed, quote unquote, than the other. It's a different shape, it's a larger size in this case. Peirce was also known for talking about what he called a kind of a tripartite form of the sign. And so there are three different kinds of signs for Peirce: the icon, which represents by resemblance; the index, which represents by dx's or points to; and finally the symbol, which represents by convention. So in our example here, fire, we have a picture of a fire. That's an icon. Index, where there's smoke, there's fire. We have smoke pointing to the idea of fire. And finally, the siren and the flashing light is an idea. It is a symbolic, because unless we live in a specific culture or know what this siren or flashing light means, it could mean absolutely anything at all. Another example would be if I asked you, what does the color pink mean? And again, we don't have enough information in this case to state what anything means specifically. And so in this case, we would need culturally, what does it mean? So then, Umberto Eco did a lot of work on Peirce's ideas. He wrote a book himself on semiotics, etc., and language as well. And Eco, of course, was known for writing books and novels, and he was an industry unto himself. But specifically, I also want to mention that I don't believe that there's a specific problem of scientific representation. So many folks will say, well, we have a model, but is it a scientific model or another kind of model? Is it a scientific symbol or another kind of symbol? And that doesn't matter. A symbol is a symbol. You know, we understand things in terms of their discourse, and we understand that a scientific model is a model of something. It makes some people uncomfortable. I understand that. But in this case, I'm going to have to state really that there is no special problem of scientific representation. So that being said, the sign, or something that represents something, is also asymptotic to what it represents. And everybody else had a graph, so I added one too. You know, really though, it shows an asymptote. It shows that, let's say the red line is the sign and the green line is its meaning, that the two will never actually reach each other, that they are cultural units, that they belong within a substrate of some sort. Also, just as an aside, the reason I used Comic Sans is because it's probably one of the most accessible fonts. If somebody has a problem reading or whatever, Comic Sans works for that. And so that's why I do that, to make my talk more accessible to others. Mieke Ball is a narratologist, and she's written a book called Narratology, where she talks about stories and how it is that we create them. She believes what we have is an archive, or the very basis, the cultural basis of a story. So if I was going to do a biography of someone, the idea of that would be that there would be an archive of 1 second per second. The parts of the story itself, are the parts that are chosen to elucidate meaning, where the narrative is actually the way that those parts of the fabula have been arranged to create meaning and are a discourse. And some narrative discourses are verbal, some are visual, some are hybrid. We're going to be talking about, in this case, a kind of a data discourse, where the discourse itself creates meaning. So that being stated, a parse data set is a kind of discourse between the learner, the data set, and the programmers, where the learning forms a kind of a meaning. The parse data set is a model or sign of something. In that case as well, what we have is the data in a data set is both an iconic and indexical sign. It points at what it represents, and it's also conventional, where the relationship between the data and the learner and the meaning is asymptotic, and it has to be interpreted by someone to mean something else. Narratologically, a data set can be seen as both the fabula and a narrative derived from that fabula. And as we can see, it represents a much larger group of people. It's also a chosen subset of the above and is therefore a narrative, and the machine learner that parses the data may be seen as a story or meaning. It's the theory-laden part, as we've been talking about earlier. So the parsed data is itself another fabula, though, because we can then take that and learn from that and further and so on. It's another narrative discourse. So to conclude, semiotics and narratology are both tools which are useful for understanding fields of meaning, that we can understand in this case how data creates meaning and data sets and all. That machine learners are probabilistic, as we know, in nature, and they create what we term narratives, which are asymptotic to the fabula that they represent. That data sets, machine learners, and the data accumulated from these may be viewed as a narrative and has a disjunctive relationship to its data set, that the relationship between science and our narratives about science will probably also have this kind of asymptotic relationship. And so the story in this case is created via machine learning. The story will always have a disjunctive relationship to what it describes. Thank you.
Thank you, Joel, and thank you to all of our lightning talk speakers. We have about 10 minutes for questions. Questions can be directed at any of the individual speakers or a combination of the speakers. Christoph.
Yes, thanks for the talks. I would have several questions, but let me just ask one question to Luca. I found your talk particularly interesting, but I was wondering, you mentioned the three categories, theory, experiment, and phenomenology. If I understood correctly, these are categories that are already built in the database, right? So I was wondering, did you try to, because you use these categories as a way of sorting the publications, right? And actually sorted, yeah, the publications were sorted, and therefore the authors were more or less sorted depending on their relative weight of publications along these different topics. But did you, and then you use these categories to extract keywords to try to understand the differences. But I mean, how solid are the categories? In other words, how about going the other way around, taking the publications without the labels, and then trying to do some clustering, try to see if the papers do cluster properly into three categories to legitimize the labels, because if the label is very well attributed to the different papers, then the signal you will be very clear. But my experience with other labels in other fields of science were that sometimes they were, so. So I was sort of wondering, yeah, did you try to check if the labeling of the papers was robust, or in one sense, in one way or another?
Yeah, so that's a very good question. And we actually had a similar question. So we performed sort of a robustness analysis that I was not able to show today. But what we did essentially was that we for other work, we clustered the literature into topics using topic models. And then what we did was to map these models into a two-dimensional representation, and then look at how they were spatially distributed according to the dominant category of the three categories that I mentioned, to which they are most associated. And what we find is that they were somewhat clustered in space according to these three categories. And so I think this sort of provides this sort of validation that you mean, right? I'm sorry, I cannot show that because, but it's on archive in the draft, right?
Okay, thanks, Jakob.
My question is also to Luca. Thank you very much for your talk, first and foremost, Luca. So one limitation that I see with similar approaches, and it has nothing to do with your particular algorithms or anything, it's just the databases themselves are like that, is that there is, of course, no discrimination between accepted theories, accepted ideas, and pursued ideas. And if we don't take that distinction into account, this distinction between what the specific epistemic agent, in this case, the respective communal agents, what they think as communally agreed upon and what they think are worthy of pursuing. And so they keep publishing things about superstrings, for instance, then it's going to skew the results, obviously. It's going to skew the results. And you see that on the slide when you talk about phenomenology and theory, but most theoreticians are worried about manifolds and strings and things like that. So of course, most of these authors would say, yeah, we don't think that there are, we don't think that the existence of superstrings is currently accepted, but we do agree that it's going to be probably the next big thing, or it's at least it's worth investing money and effort. So my question is, do you think there are any ways, linguistic analysis or any sort of ways to distinguish between the ideas that are accepted by that respective agent at that particular time and the ideas that are merely pursued?
I think it's a very good question. So we were more interested in how the practices of different groups are related to each other. And so that's why we didn't make the distinction, but I think it would be difficult. I mean, so first our material was the abstracts. So that's of course the main trouble. But I mean, if you were interested in doing that, yeah, even in full text articles, and then even I don't know, because I mean, what tends to be accepted tends to also be sort of latent. I mean, I don't know how to say that. Or implicit. And so that makes it even more difficult. So I don't know, we need to think more about it.
Perfect, thank you.
Okay. Guillermo, you had your hand up before?
Yeah, I wanted to say, yes. Okay, I can say that because it was already mentioned in the reply by Lucan, is that, for example, Dimensions is a database that does that, or that kinds of solve the problem of the categorization of publications, because it doesn't label the publication according to a list of categories they have. Instead, they go inside the document, and with an artificial intelligence algorithm, they read the paper and extract the concepts. And based on that, they categorize the content of the paper. Then, for example, if you publish something in Nature, it's not multidisciplinary, because Nature is multidisciplinary. It depends on the content of the paper, and then it could be chemistry, physics, biology, or sociology, or something like that. That was something I wanted to add.
Okay, great. Thank you so much. All right, so that's all the time that we have. Let's thank again our speakers.